I'm going to show how to use figure A15 from the textbook, thermodynamics textbook, to determine the compressibility when pressure and temperature of the gas are given. The compressibility chart is used to determine whether the gas behaves like an ideal gas or it's far from it. And after determining the compressibility, if it's close to 1, then that can be used as a correction factor, and then the simple ideal gas equation of state can be used to determine the unknown property. I have copied figure A15 and also table A-1, and I'm picking methane gas at, let's say, 287 K, and the pressure is 14 megapascals. So looking at the compressibility chart, we have to determine P reduced pressure, which is defined as given pressure over the critical pressure. And also we need to determine reduced temperature, which is given temperature over critical temperature. So the given pressure is 14 megapascals. I'm not going to convert it into kilopascals because critical pressure in table 1 is given in megapascal as well. So looking at the value of critical pressure for methane, I'll see that it is 4.64 megapascals. So the answer will be approximately 3. That's the reduced pressure. For temperature, the given temperature is 287 K, and from the table A1 we'll see that the critical temperature is 191.1 Kelvin. So 287 divided by 191.1 is equal to approximately 1.5. So now I have my reduced pressure and reduced temperature. So reduced pressure is the value on the horizontal axis on figure A15. Compressibility chart Z can be determined from the vertical axis. And these green solid lines. So there are two types of green lines here. The solid lines are actually constant temperature lines. The dashed lines are constant specific volume lines. These are constant specific volume lines in purple. So locate reduced pressure of 3, which is here, and we need to find the reduced temperature curve corresponding to the value 1.5. So this is the reduced temperature line corresponding to 1.5. So if I draw a vertical line from TR value of 3 until it crosses the TR value 1.5, then I can determine the value of Z as 0.8. So the compressibility factor for this gas at the given condition is 0.8. It means that if we want to use the ideal gas equation of state, we have to use a correction factor of 0.8. For example, if temperature and pressure are given, we can then determine specific volume knowing the gas constant for that gas, in this case methane, and applying 0.8 as compressibility factor, we can determine its specific volume. So in this case, specific volume is equal to ZRP divided by P. Keep in mind that this has to be in kilopascals now. The answer is 0.8 times gas constant is here, 0.5182 times temperature 287 divided by pressure converted to kilopascals is going to be 14,000. So the answer is 0.0085 to the cube per kilogram.